Hi, this is 6.6 logarithmic and exponential equation. You might want to make a full-size screen on this one, especially because the fonts are a little small because I had to get a lot of writing in here. So this is basically four different types of logarithmic and exponential equations that you're going to see in this section. And so this is going to give you practice of how to solve these types. Now, the first one I set up as logarithmic expressions equaling a number. So basically what you end up having is you got logs and numbers coexisting in the same equation. So what you're going to have to do is get all the numbers on one side and all the logarithms on the other side. And so what you want to do that's what first step is going to say. Then change to exponential form after you wrote it as a single logarithm. So when you write it as a single logarithm, you're going to have a log equaling a number. Okay, so and at that point you solve the equation and then check for domain errors. Remember, sometimes what happens is you solve these things, they don't really have a solution, and you have to put that number back in to confirm or deny whether that's going to work or not. So when you put that number back in, you get a negative number. So you're taking a log of a negative number, then you got to throw that number out. So um, remember, negative numbers doesn't mean it's always bad, and positives doesn't mean always it's good. You've got to check it to see if it's allowed or not. So if the -2 is put in for the x, but it turns out that you're taking a log of a positive number, then everything is good. So that's what the main thing is. And part B, logarithmic expressions equal logarithmic expressions. So there's no numbers involved in this problem. It's just logs on one side and logs on the other side. Sometimes you can have one or two or maybe even three logs on one side and one or two or maybe even three logs on the other side. And what you're trying to do is compact it down. So there's no numbers involved, just logs plus logs, logs minus logs. So what you do is use your product rule or your quotient rule or your power rule to write each side as a single logarithm. At that point, you drop off the logs and then you solve the resulting expression, which is like you always have done. So, and that's what it says here. Write each side as a single logarithm, drop off the logs, solve the equation from step 2, and then again check for domain errors. So that could happen again. That you may not you be able to use the solution that you ended up with. Now, part C I put under one category, but what happens is it's exponential equal exponential or exponential equaling a number. They both work exactly the same way. So what you do is you take the natural log to both sides. Okay, what happens is when you're going to have a log of something with a power, well, you're going to take the power right in front. So use the power rule to write powers as factors. If you recall from the previous section, I also talked about the change of base formula. You could also use the change of base formula at this point as well. Some people choose to do that technique, and that works. Okay, and in class, I'll show you how that works. In class, I'm just going to do this a different technique here. So you're going to have to come to class to see how the change of base formula works for that. And then how to use your power rule, isolate the variable by manipulating to get to x by itself. The book or in my math lab might ask you for a 2 decimal or 3 decimal approximation, so keep that in mind as well. Part D, exponential in quadratic form. This is a very small piece of this section. You may get one or two problems on your in your My Math Lab homework. Probably in debate whether I even give you one on the test or not, but you need to be prepared just in case. But you're using substitution to solve, and we're going to back substitute, then use the same procedure as we did in C. So definitely the most challenging one of the bunch. So, okay, so let's begin with example 1, which is an illustration for part A. Example 2 is going to illustrate part B. Example 3 is going to illustrate part C. And example 4 is going to illustrate part D. Okay, so keep that in mind. So log base 2 of x plus 1 plus log base 2 of 5 equals 1. Noticing there's a number on one side and there's logs on the other side. So we're going to write each side as a single, write this side as a single logarithm. So using the product rule, because log plus a log is the log of the product. So this is going to be the log base 2 of 5 times x plus 1 equals 1. So it's the log of the product. Once you got that in single logarithm, change the exponential form. So it's 2 to the first equals 5 times x plus 1. So 2 equals 5x plus 5. I think, yeah, distribute the 5. 2 to the first is 2. Now subtract 5. Subtract 5. So it'll be 5x equals 2 minus 5 is negative 3. And then negative 3 divided by 5, so x is negative 3/5. Now notice the answer is negative 3/5. At first glance, you're just going like, oh, it doesn't work because it's negative. And a lot of people say it's negative 3/5, it's not going to work. But when you put negative 3/5 back in, negative 3/5 plus 1 is a positive 2/5. And positive 2/5 is fine, it's positive. And definitely log base 2 of 5 is going to be okay. So this is the one I wanted to show you because sometimes the answer is negative. And it's very tempting to throw it away because of its negative. So, but this one is works. So negative 3/5 is a legal solution. All right. Now example 2 is going to illustrate this one. We have logs on both sides. So what we're going to do on the left side, log of x plus the log of x minus 4. So this is going to be written as the log of x times x minus 4 on the left side product rule. And on the right side is just going to be the log of x plus 6. So, all right. Then you got logs on this side and log on this side. Since logarithms are 1-to-1, we'll have to discuss that in class again, but you drop off the logs. So it's x times x minus 4 equal to x plus 6. So now it's just a matter of solving for x. So this goes back to chapter 1 stuff. So this is going to be x squared minus 4x, distribute the x, equals x plus 6. Subtract x, so it's going to be x squared minus 5x. And then subtract 6. And you get x squared minus 5x minus 6 quadratic. So we factor this, and it factors to x minus 6 times x plus 1 equals 0. So x equals 6, and x equals negative 1. Maybe, okay? Because these numbers might not be allowed. Let's put 6 back in and find out. If you put 6 in here, that's fine. 6 minus 4 is 2, that's fine. 6 plus 6 is 12, that's fine. All those numbers were positive. Put negative 1 in. Now, even though negative 1 works for the last one, negative 1 plus 6 is 5, and that's fine. The negative 1 is not going to be okay here because that's going to be a negative 5, and it's definitely not here okay either. So the negative 1, even though it's a solution to this equation right here, it is not a solution to this equation. So the x equals negative 1 has to be discarded. So you don't write no solution because there is a solution. It is 6. Now example 3, okay, 2 to the x minus 1 equals 3 to the x plus 1. This is an example for this one. As a matter of fact, it's exponential equals an exponential. Now this one here is 2 to the x minus 1 equals 3 to the x plus 1. Now if you remember back in earlier in chapter 6, we were able to solve these types of equations easier because the bases could be made the same. Because back in that section we would have something like here 2, and something like here would be like 8, and you'll change 8 to 2 cubed. And then you can make the bases the same and you can set the exponents equal to each other. Well, you can't do that here because 2 and 3 cannot be made or manipulated to have the same base. So we needed a new technique. So if you remember back in that section, I showed you there's going to be something later on in chapter 6 that we're going to hit that can't happen. Here it is. So 2 to the x minus 1 equals 3 to the x plus 1. So the technique is take the natural log of both sides. You're like, why natural log? Well, I can use any log I want, but since natural log is a button on the calculator, I'm going to need the calculator to get a decimal approximation. So I'm going to have to use a natural log or a common log. So, and I'm going to choose natural log over a common log for something that you guys probably found pretty silly. But you will see it later on. But the natural log, I use it over common log because it has one less letter in it. Log has 3 letters, ln has 2 letters. Sounds kind of silly, but sometimes you have to write these things down when you're trying to solve the equation. Sometimes you write out on the lines of 20 times. So if you write ln 20 times and log 20 times, that extra letter does seem to add up, especially if you're multiplying that by 10 to 12 to 20 problems on homework. So anytime it saves you a little bit of time, go for it. So ln over log simply because one less letter, that's all. So now I'm going to take the natural log of both sides. So ln of 2 to the x minus 1 equals ln of 3 to the x plus 1. Then using the power rule, I'm going to write powers as factors. So this becomes x minus 1 times the natural log of 2 equals x plus 1 times the natural log of 3. Now, some people have some strong prejudice against the distributive property. I don't know why. I don't know if they just don't know what to do it or don't want to do it, but a lot of people will not want to distribute these logs through. I have found that it's probably the most simplistic way to do this problem, although it can be solved other ways. You can divide by the natural log of 2 over here, and you can divide by x plus 1 over here, which is a lot of people will choose to do that, and because they don't have to worry about that multiplication. But the problem with that is you have x minus 1 over x plus 1 on one side, and you got a fraction of ln of 3 divided by ln of 2 on the other side. And that creates more problems than it's really necessary. So what I do is I distribute the logs on both sides and then rearrange the terms. So you get x the natural log of 2 minus the natural log of 2 equals x natural log of 3 plus natural log of 3. So it's just a matter now of just playing musical chairs with the terms. Anything that has an x in it, you put on one side. Anything that doesn't have an x, you put on the other side. Let me go back up here so you guys can all see this. So we'll have x natural log of 2 minus x natural log of 3. Because I moved this natural log of 3 to the other side, and the negative natural log of 2 I moved to this side, plus the natural log of 3 on this side. Now the right side is easy because that's just the natural log of 6. Natural log of 2 plus natural log of 3 is natural log of 2 times 3. Make things simple when you can. And then this is x factored out, natural log of 2 minus the natural log of 3. And to isolate the x, you divide by this quantity. So x equals the natural log of 6 divided by the natural log of 2 minus the natural log of 3. And yeah, natural log of 2 minus natural log of 3 is the natural log of 2/3. I'm not so anxious to write it that way because of the fraction. So, and I can plug this into a calculator pretty easily anyway. So you got a couple of choices. You can divide natural log of 6 divided by the natural log of 2 minus the natural log of 3 in parentheses. Or you can take the natural log of 6 divided by the natural log of 2/3 using the quotient rule on a calculator. Either way will work, should give you the same answer. So, but anyway, if you get it as a decimal, and I'm not going to do it here, and what that basically is, you put that number in here, and then make the left-hand side equals to the right-hand side. And that's the idea. The idea is trying to figure out what x has to be to make the two sides equal. So what you have to do, take the natural log of both sides, bring the powers down. The hardest part is right through here. This work right in here is what kills people. But you get past that, put the x's on one side, and then factor it out and divide it through the other side. So not easy. Okay, it does take a little bit of time, a little bit of effort, and a little bit of patience. So you have to use all three of them. Now this one right here is the fourth one, D. 3 to the 2x minus 5 times 3 to the x minus 6 equals 0. So what I'm going to do is I'm going to let my delta, remember delta, and it's equals to 3 to the x. And then it makes delta squared 3 to the 2x. So this becomes delta squared minus 5 delta minus 6 equals 0. And if you look at that, that was the exact kind of situation I had in example 2. So I like to say that I did that on purpose, but that was kind of accidental. So that's going to be delta minus 6 times delta plus 1 equals 0. So delta equals 6 and delta equals -1. So that's what delta is. And then you go back and you put 3 to the x back in. So you get 3 to the x equals 6 and 3 to the x equals -1. Well, the right one, 3 to the x equals -1, is not going to be solvable because this is exponential expression. Remember, exponentials look like this. -1's down here. 3 to the x will never hit -1 because -1's down below. So this one's not even going to work. You know, I wouldn't have saw that. Well, just take the natural log of both sides and then attempt to take the natural log of -1 and see what happens. So natural log of -1 is going to give you an error. So, but that's what you can do here. You can take the natural log of both sides. So the natural log of 3 to the x equals the natural log of 6. And actually, this is an example of exponential equaling a number. It works exactly like example 3 did here, except you don't have as much work to do. Because the natural log of 6 is just that. And then x brings down, x natural log of 3 equals the natural log of 6. And then divide by the natural log of 3 to the other side. You get x equals the natural log of 6 divided by the natural log of 3. Pull out the calculator, get the decimal if they request that. If not, you'd be done. So, but anyway, so this is logarithmic and exponential equations. So every case is represented here. Now, some of the problems in this section are a lot more difficult than what I'm showing you here. So I want you to understand that this is kind of doable problems. Not every problem is going to be this easy, but I showed you the technique. Okay, the actual algebra could be more difficult here. So the actual calculations in order to move things around might be a little bit more strenuous. But you understand this is the procedure on every single one of them. So that's 6.6.